So you want to fly. Cool. If you're watching this, you've probably already learned about airfoils and lift generation. If not, feel free to check out my previous video after watching this, but today I'm going to be talking about propulsion, or how we actually move forward. To do that, we make use of Newton's third law. We throw something backwards or can push off something. Simple, right? One option is to bring your own stuff to throw. That's a rocket, which works great, but rockets have to carry both fuel and oxidizer. How much oxidizer depends on the fuel, but it's always a lot. If you're burning kerosene, you need about 2.5 pounds of oxygen for every pound of fuel. If you're burning hydrogen, you need 4 to 8 pounds of oxygen per pound of fuel. Either way, you're hauling way more oxidizer than fuel, and that limits how long you can fly, typically just a few minutes of powered flight. But what if you could just use the air that's already there? Grab it, use the oxygen in it to burn your fuel, and chuck it out the back. You'd only need to carry fuel, not oxidizer, and now you're both throwing something and pushing off the air around you. That would let you fly for hours instead of minutes. That's air-breathing propulsion. There are several different ways to do this, and each one works best in different situations. Some are mechanically simple but only work at high speeds. Others are more complex but can operate across a wide range of speeds. Let's get into it. But first, a quick heads up. Propulsion is a wide-reaching, applied field encompassing thermodynamics, fluid mechanics, materials science, chemical engineering, and more. So, in this video, I'm only going to be barely scratching the surface. We're also going to make some simplifying assumptions along the way. This will help with understanding the fundamentals without getting lost in the weeds. Real engines are way more complicated, but these assumptions let us capture the essential physics. At the core, understanding air-breathing engines means obeying some physics: conservation of mass, energy, and momentum. Imagine drawing a control volume around the engine. Air flows in the front at some velocity and exits out the back. The engine adds energy, usually by burning fuel, to accelerate that air. This results in a reactionary force on the engine forwards. This is thrust. The thrust force is equal to the exit mass flow rate times the exit velocity minus the free stream mass flow rate times the free stream velocity. For air-breathing engines, the mass flow rate in and out is roughly the same. We're adding fuel, but that's a small fraction compared to the massive amount of air flowing through, so we can simplify this. This is the momentum thrust. It says the force you generate depends on how much air you're moving, the mass flow rate, and how much you speed it up, velocity change. One more thing. The full thrust equation actually has two terms. There's the momentum thrust we just discussed, plus a pressure thrust term. Exit pressure minus ambient pressure times the nozzle exit area. When the exit pressure matches the ambient pressure, called matched conditions, that pressure term goes to zero and we're left with just momentum thrust. Most engines are designed to operate near matched conditions at their typical cruise speed and altitude. So for this video, we're going to assume matched conditions. Just know that in reality, engines operate across different altitudes and speeds, so that pressure term does matter. We're ignoring it to focus on the fundamentals. Okay, so looking back at the equation for momentum thrust, there are two ways to generate a large thrust. Take a large amount of air and increase its velocity by some amount, or take a smaller amount of air and increase its velocity by a very large amount. Both approaches could theoretically give you the same thrust, but, and this is crucial, they have very different efficiencies. That efficiency difference is what drives the selection of air-breathing propulsion methods because not all engines are created equal. Depending on what you're trying to do, you care about different performance metrics, and you'll design your aircraft entirely differently. A change to one aspect of the aircraft has cascading effects on the rest. For the purposes of this video, when we talk about performance drivers, we'll assume everything else about the aircraft is held constant. But you should know that this is almost never the case when looking at trade-offs. With that said, let's look at the major performance metrics and their key drivers. The first driver is thrust-specific fuel consumption, or TSFC. This measures engine efficiency, how much fuel you burn to produce a given amount of thrust over time. Different engines have very different TSFC values, especially at different flight speeds, which is why this driver has a major impact on a key metric: range. How far can you fly on a tank of fuel? This is critical for everything from cargo planes to long-haul airliners. Range depends on several factors that get captured in the Breguet Range Equation. It tells us that range depends on your fuel efficiency, or TSFC, at a given speed, your aerodynamic efficiency, lift-to-drag ratio, and how much fuel you're carrying relative to your total weight. Assuming all else is held equal, more efficient engines directly translate to longer range. This also means less fuel is needed on board, leading to further range. This is why the shift from turbojets to high bypass turbofans was such a game changer for commercial aviation. You could suddenly fly across oceans without refueling. But range isn't the end-all be-all. The next performance driver is the thrust-to-weight ratio. This is exactly what it sounds like: your engine's thrust divided by the aircraft's weight. Thrust-to-weight ratio directly impacts three key metrics: takeoff distance, climb rate, and maneuverability. Higher thrust means you accelerate faster and therefore can achieve takeoff speed and get airborne sooner. This is key for things like carrier-based aircraft. More excess thrust that's beyond what's needed to maintain your level flight, means you can climb faster. Fighter jets need high thrust-to-weight ratios to pull high G turns and accelerate quickly. In fact, if the thrust-to-weight ratio is greater than 1 and the drag is small enough, the aircraft could theoretically accelerate straight up like a rocket. A commercial airliner might have a thrust-to-weight ratio around 0.25 to 0.3, while a fighter jet could be 1.0 or higher. Different missions, totally different requirements. The last driver we'll cover today, but there certainly are more, is called propulsive efficiency. For a given amount of thrust, it's more efficient to accelerate a large mass of air by a small amount than to accelerate a small mass of air by a large amount. The reason comes down to how much kinetic energy ends up in the exhaust versus how much goes into moving the aircraft forward. The closer your exhaust velocity matches your flight speed, the better your propulsive efficiency. If they matched perfectly, you'd have 100% propulsive efficiency, but you'd also have zero momentum thrust. No thrust means you can't overcome drag, so the aircraft would slow down. So there's always a trade-off. You need the exhaust velocity to be higher than your flight speed to generate thrust, but the bigger that difference, the lower your propulsive efficiency. This leads to the fundamental tension in propulsion design. You can build an engine that produces tons of thrust and is very efficient, but it will be a behemoth. Or you can achieve that thrust while sacrificing efficiency for a smaller, more compact engine. You can get the same thrust by moving lots of air slowly, high propulsive efficiency, but physically large, or moving less air quickly, lower efficiency, but more compact. Every aircraft design is optimized around these trade-offs based off its specific mission. A cargo plane crossing the Pacific needs maximum range and efficiency. A fighter jet needs high thrust and maneuverability. When we get into supersonic territory, above Mach 1, the trade-offs change again. That's why we have so many different engine types. Each one occupies a different spot in the performance space. Now that we understand the key trade-offs, we can return to the original question. How do we actually add energy to the air? That's what separates one type of engine from another. The first practical method, and still one of the most efficient for lower speeds, is the propeller. A propeller acts like a rotating wing. It sweeps through a large disk area and accelerates a massive volume of air backward by a relatively small velocity change. At typical cruise speeds for propeller aircraft, about 150 to 300 miles per hour, the velocity added to the air is relatively close to the aircraft's flight speed. This means excellent propulsive efficiency, often 80 to 85% or higher. But, and there's always a but, the limitation is that as you go faster, propeller blade tips start approaching the speed of sound, causing compressibility effects and shock waves that kill efficiency. Propellers also create a lot of drag at high speeds, so if we want to go really fast, we needed something different. Enter the turbojet. Instead of a big propeller out front, you have a gas turbine engine that does everything internally. Air gets sucked in, compressed by rotating compressor stages, mixed with fuel and burned, then expanded through turbine stages that power the compressor. The hot, high-pressure exhaust shoots out the back at very high velocity, often over 1,000 miles per hour relative to the engine. This high exhaust velocity is great for generating thrust at high speeds. It's what lets us break the sound barrier and reach supersonic flight. But here's the catch. At supersonic cruise speeds, say 500 miles per hour, you're accelerating air by around 800 miles per hour. That's a huge velocity difference, which, as we discussed, means low propulsive efficiency, typically only 50 to 60% for subsonic flight. You're wasting a lot of energy creating fast-moving exhaust that doesn't contribute efficiently to thrust, so we needed a middle ground. The turbofan was the solution to this efficiency problem. The core idea: keep the gas turbine engine in the middle, but add a large fan up front. Most of the air pulled in by that fan doesn't go through the engine core at all. It bypasses it. This bypass air gets accelerated by a moderate amount and exits at a much lower velocity than the core exhaust. Meanwhile, a smaller amount of air goes through the core, gets burned, exits at a high velocity. The ratio of bypass air to core air is called the bypass ratio, and it's the key metric for turbofans. Low bypass turbofans, with bypass ratios of 1 or 2, were developed first in the 1960s. They offered better efficiency than pure turbojets while still working well at transonic speeds. These are what you'll find on many military fighters. High bypass turbofans came later, with bypass ratios of 5, 8, even up to 12 on modern airliners. These move enormous amounts of air at lower velocities, matching the propulsive efficiency concept better for subsonic cruise. This is why they dominate commercial aviation. They're significantly more fuel efficient than turbojets for the same thrust at subsonic speeds. Think of it this way. A high bypass turbofan is trying to act more like a propeller. Lots of air, small acceleration, but still enclosed and efficient at higher speeds than a prop could handle. But this comes with a much larger size. What if you want to go really fast, like supersonic or hypersonic? At very high speeds, the complex turbo machinery, all those rotating compressors and turbine stages, become a liability. The air coming in is already moving so fast that it naturally compresses when you slow it down. So why not use that? That's the ramjet principle. No compressor, no turbine, no moving parts. Just a carefully shaped duct. The aircraft's forward motion rams air into the inlet. The duct shape slows it down, converting velocity to pressure. Fuel is injected and burned, and the exhaust accelerates out the back. Here's a surprising fact. This concept was actually invented way back in 1913 by René Lorin, before turbojets even existed. But ramjets have a fundamental limitation. They don't work from standstill. You need to already be moving fast, typically above Mach 0.5 or so, for the ram compression to be effective enough. They typically work best between Mach 2 and 5. So while the concept was simple and came early, ramjets had to wait for the right applications. They found their niche in missiles and high-speed experimental aircraft, where they could be launched by rocket boosters or dropped from another aircraft. Scramjets take this even further. In a regular ramjet, the incoming supersonic air is slowed down to subsonic speeds before combustion. But at hypersonic speeds, Mach 5 and beyond, slowing the air down that much creates huge pressure and temperature loads. A scramjet, supersonic combustion ramjet, keeps the airflow supersonic throughout the entire engine, including during combustion. This allows operation at hypersonic speeds, potentially up to Mach 15 or higher. They also only work at very high speeds, typically above Mach 5. As of now, scramjets remain mostly experimental, tested on vehicles like NASA's X-43 and the X-51, but they represent the cutting edge of air-breathing propulsion research. So that's a certainly not exhaustive glimpse into the landscape. Propellers, turbojets, turbofans, ramjets, and scramjets. each one optimized for different speed regimes and mission requirements. In future videos, we'll dive deeper into each of these, the details of how they actually work, their performance characteristics, and where they're used. I'm also planning videos on combustion cycles and electric propulsion. If you want to see those, hit that subscribe button, please like this video so others can find it too. Thanks for watching, and I'll see you next time.